Topic 1. Atoms, molecules and ions. In this presentation we're going to be learning about the building blocks of chemistry, the atom and what the atom is made up of and what happens when we combine atoms. So what is an atom? Everything around us is made up of these things, so it might help if we know a little bit about them. They're the smallest building block chemically, so we might be able to break an atom down into its smallest parts, but that's generally not what we do in chemistry. In chemistry, the smallest building block is an atom. And each atom is made up of subatomic particles, and these subatomic particles are called electrons, protons and neutrons. These are the basic ones anyway. In physics we might have lots more subatomic particles, but in chemistry these are the only ones that we're really concerned about. So you can see here that in the nucleus we have the protons and neutrons, and the nucleus is surrounded by a large cloud where the electrons might be found. So key things to note about these particles, the electrons, protons and neutrons, is their symbol, their relative mass and their relative charge. So an electron has got a relative charge of -1 and a proton has a equal but opposite charge of +1. However, the electron has virtually no mass compared to the proton and the neutron. The protons and the neutrons are what gives an atom its mass. So they have a relative mass of 1 each, whereas the electron has a relative mass of a lot smaller than that, 5 times 10 to the -4. So we virtually say that an electron has no mass when we're talking about relative mass terms here. And the charge on the neutron is, as it sounds, it's a neutron, so it's neutral, so it's got no charge, 0. But again, as I mentioned, the mass of the neutron is equal to the mass of the proton. So protons and neutrons are found in the centre of the atom, electrons buzz around the outside and are indicated here as a cloud around the nucleus. So depending on how many protons we have in a particular atom would give us a different element, and there's 114 elements that have been discovered so far, and these are listed on our periodic table, which you can find in the resources folder. So here's some common elements that you might have heard of before. We've got magnesium, calcium, iron, aluminium, silicon and oxygen. These are all found in the Earth's crust in quite a high abundance. And then we have other elements which can be found in the human body in quite high amounts, such as oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, all these common elements that you would have heard of before. Now you can put atoms to names, for example. These are all different types of elements. So what is a molecule then? A molecule is formed when we join two atoms together using a chemical bond. And a molecule can contain atoms of the same type. For example, hydrogen exists as H2, 2 hydrogen atoms joined together, or we can have different types joined together, such as in water we have 2 hydrogen atoms and 1 oxygen atom. So here's some examples that you would have heard of before, such as hydrogen, water, H2O, ammonia, NH3, and methane, CH4. Now these are all joined by covalent bonding, and in a later topic we're going to learn about the difference between covalent bonding, ionic bonding and metallic bonding, but for now just know that molecules are a result of covalent bonding, and again we'll expand on that later on. So just some other terms here to define that you may come across in your reading. A compound, which is any substance which is made up of 2 or more elements in fixed proportion, so we can have things like salt, like sodium chloride, or water. We can call both of these species compounds. Physical versus chemical properties. So the physical property is things like density or the boiling point, for example. So these are properties that don't change the compound. For example, if we change water from liquid water to steam, it still stays as water. Whereas a chemical property is when we actually change the substance into something else. So if we react sodium with water, we get new compounds produced. We get sodium hydroxide, and that's completely changing the structure of water. So that's what we call a chemical property, the actual reactivity. So let's have a closer look at how elements and atoms are represented. And because we talked earlier about these particles, electrons, protons and neutrons, we have to have a way in which we represent elements and atoms. So here we've got a little box, and that's to indicate how a element may be shown on the periodic table. That 6 above the carbon there is the atomic number, so that's the number of protons. The C is the letter symbol, which is different for each element. Then there's obviously the name of that element and the atomic mass. So this is the mass of 1 mole of, in this case, carbon, and we'll be learning about moles when we do topic 3, but for now, just knowing what that number stands for. And we can also represent an element here using the X, A and Z kind of nomenclature. The X is where the symbol goes, so if it was carbon that would be C. The mass number is indicated by A, which if it was carbon would be 12, if it was an isotope of carbon-12. And the atomic number Z there is indicated by the number of protons, which obviously is the atomic number 6 for carbon. So the mass number is the number of protons and neutrons, and this changes depending on what isotope we have, which we'll learn about in a minute. But some examples that we've got here of the way that these atoms might be represented are hydrogen, H11, carbon, C12-6, magnesium, 2412, and uranium, 238-92. So there's just some examples of how we represent some different elements. So you heard me mention isotopes, and we're just going to expand a little bit on isotopes here. Isotope is simply when we have the same element, but it has different numbers of neutrons in that element. So here we're saying that the number of protons in a given element is always the same. So if we have an element of carbon, no matter what isotope of carbon we have, it will always have 6 protons in it. Or hydrogen, for example, always has 1 proton. However, the number of neutrons changes, and because the number of neutrons is changing, that means that the mass of the element is changing. So you can see here that we've got isotopes of hydrogen here. We've got hydrogen with 1 proton and no neutrons, and that's the most abundant isotope of hydrogen that we're used to. Then there's deuterium, which has 1 neutron and 1 proton, and it's obviously called deuterium because it's got a mass number of 2. And then tritium with a mass number of 3 because it's got 2 neutrons and 1 proton. But in each case there you can see that each isotope of hydrogen, even though we call it different names there, they all have 1 proton. So some applications of isotopes are carbon dating. And the way that carbon dating works is that we have nitrogen in the atmosphere converted by a high energy cosmic ray into carbon-14, which is a radioactive form of carbon. And what happens is that carbon is incorporated into carbon dioxide in the atmosphere, and then that is absorbed by plants, and then we eat those plants, and it continues to decay. But as long as we keep breathing and we keep on eating plants, etc., we will maintain the same ratio of radioactive carbon to non-radioactive carbon. And then once we die, obviously that radioactive carbon that we have left in our body is going to slowly decay away until we get to the point where we don't have any radioactive carbon left. And we can then work out how old a species is, which was once living, solely based on the ratio of carbon-14 to carbon-12. And the half-life of carbon-14 is around just under 6,000 years, which means we can only date things using carbon dating that are around that age. So we also use isotopes all the time in medicine. So we can use radioactive iodine or other radioactive compounds in medical imaging or in radioactive tagging to see how certain species might move through our body. And obviously we can use isotopes, radioactive isotopes, in nuclear power. So we've got there 2 different isotopes of uranium. So the key that you have to recognise with isotopes is that sometimes that we can omit the lower atomic number. So for example, carbon-12-6 becomes simply carbon-12. And the reason that we do that is simply because as long as we have the symbol there for carbon, we know that the number of protons, 6, is always going to be 6. So we don't need to write it in there. So here's just some practice to be able to find the number of protons, neutrons and electrons in some isotopes. So if we've got an isotope of carbon-14, from the periodic table we know that carbon has 6 protons. So if it's not given, just use your periodic table to look it up, and in the GAMSAT you'll be given some condensed version of the periodic table, or you'll be given the atoms listed with their proton numbers or their atomic numbers. If it's a neutral element, it's always going to have the same number of electrons as protons. So therefore, a neutral isotope of carbon-14 will have 6 protons and 6 electrons as well. Now the neutrons is the only thing that ever changes, and to work that out we simply use the mass number, take the number of protons to work out the number of neutrons, which in this case is 14, which is the mass number, minus 6, which is the number of protons, equals 8. So 8 is the number of neutrons. If we have a look at carbon-13, you can see that with one less mass number, the neutrons are one less as well. So there's only 7 neutrons in an isotope of carbon-13. And then you can do the same thing to work out the number of neutrons in uranium-238 isotope. So here's a little question here. Why are the atomic masses for elements listed on our periodic table not whole numbers? For example, hydrogen is not just 1 and carbon is not 12, it's 12.01. Well, we have to remember that in nature, small amounts of these other isotopes, so for example for carbon, there is small amounts of carbon-12, carbon-14 and carbon-13. And those small amounts contribute to the average mass. So this average mass that we see on the periodic table is just the average of all of the naturally occurring isotopes. So that's why the mass of carbon is slightly a bit higher than 12. It's 12.01. That's because of the contribution of those other isotopes that are present in nature. So through my presentations you're going to get a good introduction to some chemistry geek jokes. So here's the first, isotopes. So you've heard me talking a little bit about the periodic table, so let's learn now about the periodic table and how it's arranged. You can download a periodic table or download an app for your phone for the periodic table, which might help you, but if you don't have one, there's one in the resources folder that you can download with all the molar masses and atomic numbers, etc. on it. But here's an example here of a periodic table which shows the metals, the metalloids and the non-metals. So all of the green zone are metals, the blue boxes are indicative of non-metals, and that little zigzag in the middle is when they start to merge into one another, and we call those metalloids. They have some properties of metals and some properties of non-metals. So something else that you need to know about the periodic table is that we call the vertical columns groups. So elements that are in the same group have similar properties, and as we'll learn in a minute, that's because they have a similar arrangement of electrons. Then there's the periods, which are the horizontal rows, and as we go along in the periodic table, as we move from left to right, every box we move from left to right and then down into the next period, we add 1 proton. And if it's a neutral element that we're talking about, then obviously we also add 1 electron as well. So that explains how the periodic table is somewhat built up. Each box we move from left to right and down and across, etc., is 1 extra proton being added. And you'll find that the structure of the periodic table is derived from that fact, and also in the way that the electrons are arranged around the nucleus, which we'll talk about over the next few slides. Okay, so you've heard me talk about a neutral isotope or a neutral element. So now let's use these words to talk about what happens when we don't have a neutral element, when it becomes charged. And when an element or an atom becomes charged, we call it an ion. An ion is an atom or a group of atoms that has a net positive or a net negative charge. And this is a result of loss or gain of an electrons. If it's a cation, it means it's lost 1 or more electrons and it's therefore positively charged. If it's an anion, it means it's gained 1 or more electrons and therefore it's negatively charged. So the key thing to note here is that the number of protons and neutrons always remains the same during ordinary chemical changes. It's only ever the electrons that are changed, lost or gained. And that's because the electrons are the things that are on the outside of the atom. The neutrons and the protons are in the nucleus, so they don't react at all in a chemical reaction. So which elements gain electrons and how many, and which elements lose electrons and how many? You can see on this table here that the position on the periodic table gives us a good indication of whether a particular element is likely to lose electrons or a particular element is likely to gain electrons. And you can see in group 1 on the left, lithium, sodium, potassium, etc., they will all tend to lose 1 electron. And then magnesium, calcium, strontium, etc., they will all tend to lose 2 electrons and become 2+ charge. Over on the far right, in the blue zone, we've got fluorine, chlorine and bromine. They will all tend to gain 1 electron. And then there's oxygen, sulfur, etc. They will all tend to gain 2 electrons and form a 2- ion. Now, the transition metals in the middle, like chromium, Cr, Mn, etc., they all have multiple states which they may lose or gain electrons. Now, you're not going to be expected to know that. There's an indication there of how they lose or gain electrons. Here's another one of my chemistry jokes indicating that if you lose an electron, you are very positive about it. So more lingo for the periodic table. We have group 1, which are called the alkali metals, group 2, alkali earth metals, and groups 3 to 12, as you've heard me mention in the previous slide, are transition metals. Group 17 is the halogens. Group 18 is the noble gases or inert gases. Now, you're not going to be expected to know all these names, but in your learning you may hear me come up with these names, so I just thought I'd introduce you to them. It's a good way to group elements with similar chemical properties as we talk about those chemical properties. So within the periodic table there's blocks. We have the S block, the P block, the D block and the F block, and these are known as subshells. And you'll find that these actually correspond to the shape of the region of space where we're likely to find an electron. And I'll show you on the next slide how the periodic table is actually broken up into these blocks, and it can really help us when we're learning about how electrons are arranged around an atom to remember where these blocks are found on the periodic table. That grey area over on the left consists of groups 1 and 2, and that's what we call the S block. Then we have the blue area, which is groups 3 through 12, that's the transition metals, and that's the D block. And then over on the far right we have the P block. Now, just something to note here, that 1s part on the top right hand corner, which is actually green, technically that belongs over on the left and is part of the S block. We'll learn about why that is later, but just take my word for it that that's a little bit of an anomaly that it appears over on the far side. And then we have the F block, which is the yellow area which you can see there. Okay, so before we delve too much more into these S, P, D and F blocks and the subshells, we need to learn about what an atomic orbital is. Now, an atomic orbital is a region of space around a nucleus in an atom that can hold 2 electrons. So no matter what type of atomic orbital we have, each atomic orbital always has 2 electrons. So these 3 atomic orbitals that you can see here are three different S orbitals. The 1s is the space closest to the nucleus, and it's in a spherical shape. The 2s, also a spherical shape, and it's just a little bit further out from the nucleus. The 3s is further out from the nucleus again. And if you skip back to the previous slide, or you can have a look, you can see that this 1s, 2s, 3s, this 1, 2, 3 corresponds to the period on the periodic table. So it corresponds to the layers of electrons around the nucleus. So the 1s means that there's electrons in an S spherical shaped orbital, which are in the first level away from the nucleus. The 2s means that we've got electrons in a spherical shape, the second level out from the nucleus. So they kind of are further out and they kind of go around the 1s, encompassing the 1s. Then the 3s is on the third level out from the nucleus. So consequently getting further and further away from the nucleus. Now the P and D subshells give rise to slightly different shaped atomic orbitals, a little bit more complicated than our simple spherical S-shaped orbitals. So the first that you can see here, the 3 across the top, are the 3 p orbitals. Now in the previous slide we saw that there was 3 s orbitals, but those 3 s orbitals corresponded to different sized orbitals on different levels of the periodic table, or different levels around the nucleus. The p orbitals, on the other hand, you can see here, on each level there are 3 different p orbitals, and that's because these p orbitals can be arranged in different orientations in space. So we could have one p orbital pointing back to front, one p orbital pointing left to right, and another p orbital pointing up and down. And that's because they're not just a simple sphere. There's only one way that you can arrange a sphere in space, and that's just the way that we draw it. But here, because we've got the p orbitals, which consist of two lobes, we can arrange those two lobes in three possible ways in space. So that's why we've got three p orbitals. So that explains why we have a bigger p block. If you go back to slide 17, you can see that the p block consists of a total of 6 electrons. So because each atomic orbital holds 2 electrons, that explains why we need 3 different p orbitals to hold those 6 electrons in the p block. Now likewise for the d orbitals, which you can see consist of double lobes, or except for the z squared one, which is a slightly different again, but those 5 d orbitals arise because we have 10 electrons in the d block. We need to house 10 electrons, which means we need at least 5 d orbitals. So therefore we have these 5 d orbitals with their lobes arranged in slightly different orientations in space. And those coordinates that you can see there, the x, y and z coordinates, are called Cartesian coordinates, and they just indicate 3D space so that we can easily show how things may be arranged in space. So something to be aware of is that these atomic orbitals, depending on what shape they are, and also depending on how far away they are from the nucleus, will have different amounts of energy. So the lowest energy electrons are found in the 1s orbital, and that's because it's the closest possible to the nucleus. The next level up, which is now when we go to the next level away from the nucleus, so it's a higher energy level as you can see here, consists of an S-shaped orbital, the 2s, and also the 3 2p orbitals. So there's the 3 p orbitals which are in the second level. So these are of comparable energy. You can see there on the diagram we've got the 2s and the 2p at a comparable energy level, and that's because they're at relatively the same distance from the nucleus. So then we go up to the next level and we have the third level out from the nucleus, which consists of an S-shaped orbital, a 3p orbital, which has obviously the 3p orbitals that we saw on the previous slide, and they are of comparable energy. Also in this third level is the 3d, the d orbitals, the d-shaped orbitals, those lobes of which there were 5 that we saw on the previous slide. And those are quite a little bit higher in energy, and we'll talk about what happens when we fill up the nucleus with electrons. We have a choice when we get to the 3d and 4s. Because those levels are quite similar in energy, we actually fill up the 4s orbital before we fill up the 3d orbital. But we'll talk about that in more detail in slides to come. So to summarise this slide, what happens when we make an element is we essentially fill electrons around the nucleus, depending on how many electrons that particular element has. So if it was carbon, it would have 6 electrons. And we start with the lowest energy orbital, and we fill up with 2 electrons in each orbital until we get to the maximum number of electrons for that element. So the way that we actually arrange electrons into these orbitals and into these subshells around a nucleus is called the electronic configuration, and it's a fancy way of saying how the electrons are arranged, how are they configured in this atom. Now the electrons are always arranged in layers, and these layers are called shells, and within those shells there's subshells, and these shells can be divided into subshells of S, P, D or F nature. The shell closest to the nucleus is what we call level 1, and we say it has a principal quantum number of n equal to 1, and that's equivalent to like the first period on the periodic table. The second shell of an atom has a principal quantum number equal to. It's the second level out from the nucleus, and the second level out from the nucleus is divided into 2 subshells, the 2s subshell and the 2p subshell, and so on and so forth. So obviously we want a bit of a notation in order to illustrate how these electrons are arranged around the nucleus. And we use this notation here, and you can see here that we've got 1s1. What does that mean? That big 1 in front of the s means the shell number, the level away from the nucleus, which is, if it's 1s1, that's the first level. The s there indicates the type of orbital, so the subshell, so is it an S-shaped orbital or a P-shaped orbital, for example. And the superscript 1 is the number of electrons that are in that subshell. So in this case we've only got one electron in this subshell. So when we're working out the electronic configuration of any element, we want to use the periodic table and the organisation of the shells and subshells on the periodic table to work out the electronic configuration and come up with a notation. So if we start with carbon, so if you get out your periodic table and identify where that is, you can see that if we build up from the very start of the periodic table up to where carbon is, we build up a total of 6 electrons. The first 2 electrons account for the first 2 boxes, so that gets us from hydrogen to helium. We need to get down to the next period and across to carbon, so we've still got another 4 electrons to account for. So the next 2 electrons are in the boxes that correspond to lithium and beryllium. So this is on the second level, and it's in the S block, and there's 2 electrons, so that's why we write 2s2. Then the next 2 electrons which end us up at carbon are over in the P block, and we build up boron and then carbon on the periodic table. So because we're still in the second level, but we're on the P block, we now have 2p, and because there's 2 electrons in order to get to our box which indicates carbon on the periodic table, that's 2p2. So practice that with those other examples there, and use the periodic table and where the S, D and P block is in order to build up and work out the electronic configuration for any element on the periodic table. Another thing that we can do in terms of electronic configuration is use not only this notation, this 1s2, 2s2, 2p2 notation, but we can also use orbital box diagrams. And these show the spin of electrons. So they show if we've got unpaired electrons or if we've got paired electrons. And this can be quite useful if you want to work out whether a compound is magnetic or not, for example. So the key is that each of the orbitals that we're talking about, whether it's a 1s orbital or it's one of the 3 possible 2p orbitals, for example, each of those orbitals, as we've indicated, only holds 2 electrons. So we indicate each of those orbitals by a single box. So for beryllium, it's got a total of 4 electrons, and you can see that if you identify beryllium on the periodic table, it's the 4th box along, so it has 4 electrons. Its first 2 electrons are in the 1s and the 1s orbital, and we show that by its notation, 1s2. And we also show that by a box, and our box has those 2 electrons, and they have opposite spins. Now the next 2 electrons for beryllium are on the next level out from the nucleus, but they're still in an S-shaped orbital because, as you can see there, lithium and beryllium are in the S block, and we just get to beryllium on the periodic table, so that means those last 2 electrons are in an S-shaped orbital on the second level, and therefore they have the notation 2s2. So we draw another box, and it's got 2 arrows in it, indicating 2 electrons with opposite spin. Now don't worry too much about this opposite spin thing. Basically it just means that if we have 2 electrons in the same orbital, the only way that they can be in the same orbital without kind of crashing into each other or something is that they must have the opposite spins. So that's just called the Pauli exclusion principle. Now as we fill up to the higher elements, the elements with more electrons, we get some interesting things happening. Let's have a look at carbon. Let's identify where carbon is on the periodic table. It's got an atomic number of 6, which means it has a total of 6 electrons. The first 2 electrons go into the 1s subshell, and there's 2 of them, so we've got that box drawn there with the 2 electrons. The second 2 electrons, like beryllium, went into the 2s2. but now carbon has another 2 electrons still. So we want to put those in the 2p orbitals, and there's 3 possible orbitals that we could put those in. So we've got a choice. We could put them in the same p orbital, as you can see there, the 2px orbital, or we could put one in the 2px and one in the 2py, so one in each of 2 of those 3 possible orbitals. So which is it? What do we do? Well, we actually put 1 electron in each of those p orbitals, each of those 2p orbitals. And the reason for that is that all of those 2p orbitals are of the same energy, they're the same distance from the nucleus, and they're the same shaped orbital. The only difference is their orientation in space. And electrons, if possible, would much rather go into their own box than go into the same orbital as another electron. They would rather have their own orbital than have to share with another electron. And that's called Hund's rule. And it means that in a subshell, the most stable arrangement of electrons is where we put 1 in each orbital, as opposed to putting electrons in the same orbital. And when we have 1 in each orbital, it means that we've got the maximum number of parallel spins, and that just simply means the maximum number of unpaired electrons. So on slide 25, we've just got a little bit more practice, and you can see there for neon, which is in group 18, it's on the far right of the periodic table, we have all of the second shell being fully occupied by electrons, and that's what we call a closed shell, or a full outer shell. If we want to write elements in shorthand rather than writing 1s2, 2s2, 2p6, etc., we can just shorten that and write the previous noble gas. So remember that the noble gases are group 18. So we just write the previous noble gas and the previous period from sulfur, which is neon, and then we continue on with our outer shell electronic configuration. That is the electrons in the outermost level away from the nucleus. Now the electronic configuration of ions works in exactly the same way. We simply add or take electrons. So for O2 minus, you can see there we've added an extra 2 electrons, and we've ended up with a closed shell, or a full outer shell of electrons. Sodium 1 plus, we've taken 1 electron away, so we end up with the same configuration as O2 minus, and the same with F minus, we've added 1 electron. So if you want, practice these oxygen, sodium and fluorine without any charges. Practice these elements when they're in their neutral form. And we can write the electronic configuration of calcium 2 plus as square brackets Ar, which is argon. So that's showing that calcium 2 plus has the same number of electrons as argon, and we say that that's isoelectronic. Isoelectronic means same number of electrons. So there's a few irregularities when it comes to when we're filling up electrons, and they are what happens when we get to the D block. So for chromium, if you identify where that is on the periodic table, it's in the transition zone. So I mentioned before that once we get to the 4th level, or once we get to even the 3rd level, we've got this similar kind of energy between the 4s orbital, or the 4s subshell, and the 3d subshell. And the reason that it's similar in energy is because even though the 4s is further away from the nucleus, it's less crowded. The 3d is a little bit closer to the nucleus, so we would expect it to be a bit lower in energy, but it's quite crowded, so those electrons more likely to go out to the 4s level, and that's why the 4s fills first before the 3d. So if you jump back to slide 17, you can see where the 4s is written. The periodic table then has the 3d subshell lined up to be filled up in order after the 4s. So it's like that whole blue zone on slide 17 has just been pushed down by 1 level. So we always fill up in order of the periodic table and the way that it's listed here. So the 3d level is actually filled always after the 4s. Now another interesting thing about the 3d subshell is that if possible, it's actually more stable if we half fill the 3d subshell or completely fill it. So if we can, we want to get a D5 electronic configuration with 1 electron in each of those 5 possible d orbitals. So if we can do that, we will take one out of the 4s in order to put it into the 3d to get a half-filled d orbital. So that's what we've done there with chromium. Or if we can completely fill the d orbital, so have a d10 configuration with 2 electrons in each orbital, and if we can do that by taking one out of the 4s, one electron out of the 4s, then we will do that. So that's what happens there with copper. So just something to be aware of, that a half-filled d orbital or a completely filled d orbital has slightly more stability associated with it. Now if you're not sure about this, I don't want you to fret about it too much. It's probably not a major component of something like the GAMSAT, but I just thought I'd put it in there in case you come across it in your study and you get confused. This is why we get these irregularities associated with some of the transition metals. So this joke here that I've got highlights a word that I actually didn't talk about earlier in the presentation, which is the degeneracy of orbitals. So you've heard me talk about the p orbitals and there being 3 p orbitals on the same level, and those 3 p orbitals, the only difference is that they have different directionality. So they have the same energy, and when they have the same energy and the only difference being their direction in space, we say that they are degenerate. That's what we're talking about when we say degenerate, and although this cartoon here indicates another meaning of degeneracy. So in this presentation we've focused on the structure of an atom and how the electrons are arranged around the atom, and in the next presentation we're just going to go a little bit deeper into the atom and learn about some of the aspects of nuclear chemistry and what happens when we have electrons moving within an atom as a result of absorbing energy. So we'll talk about all that in the next topic, topic 1.2.